Hello, ladies and gentlemen. Welcome to our first stream that will be continuation of our and supplementation of our lectures that had to be rescheduled because of issues that are happening. And today we started later, but hopefully that will be an isolated case. Usually we'll be starting earlier. And of course, the main issue will be that this today transmission will be very short, preferably short, just to complete what was said on the last lecture that's already available on the channel. And hopefully it wouldn't be too boring. Just to cover what we did on the last lecture so everybody can easily follow. What we did was that we started with the general tools of Bayesian analysis. So we've started with certain examples from how everything works. In particular, this spell checking example, how to check if given was correctly specified. This is an example from the Gell-Mann book. And we've covered general ideas of prior predictive distribution. We did a discussion of how we can predict model behavior and use uncertainty to predict certain information with the use of prior and posterior predictive distribution. We did some tests with automatic control example. We've evaluated uncertainty of the linear quadratic controller, and of course we discussed some general ideas with variable transformation, stuff like that. And then we started discussion of single parameter models, starting with the simplest model, binomial model. So a model when we do multiple tries and we try to get from those tries, and those tries are using those tries we want to estimate the probability of an event. We did an example of testing a planet where on this planet we had just tested the what is the coverage of the planet with water with the tough experiment of dropping a probe on the planet as in the Mass Effect the game, and we did the we tried to estimate determining have we hit water or not, what is the coverage of the entire planet, and we got the general idea of likelihood. What was actually interesting is that if we use the uniform prior, that is, we've declared complete ignorance of what is happening in the probability of what's going on the planet, we get very simple posterior, which takes a form of beta distribution. What is kind of interesting is that posterior distribution and likelihood are exactly the same function with the respect to a constant, because this function, or not the same function, but the same formula. This formula looks exactly the same, has a parameter theta and values y and n. However, the likelihood, the binomial likelihood, for it is its dependent variable is y and its independent variable is theta. In case of posterior distribution, we have completely opposite set. Our dependent variable that we want to estimate from the data is the theta, so the coverage of the planet with water, and y is our data. So we've have the same formula, but we've changed the inputs, and because of those inputs, our likelihood generated our posterior, which was the issue is that it did not include any prior information because the prior was uniform. And we discussed a few words about posterior summarization, how we can do it, and discussed something about interval summaries and that they can have some problems when working with multimodality. I'm trying to find a spot to put a camera so it won't conflict with the image, but we'll see how it works later. Okay, so this was our summary for the and we've ended here. We've discussed that in case of our model, we have proclaimed complete ignorance. We did not know about anything about the planet, about our experiment before the start of the experiment. And this is rarely the case. We usually know something. And knowing something gives us possibility to introduce that knowledge into the model. And generally priors, so prior distributions, give us some kind of probabilistic quantization of our information regarding the considered problem. What is important in this case that we can interpret priors in multiple ways, because despite the fact that we have some knowledge, we want to know what kind of understanding of our knowledge is happening here. This is especially important when discussing differences between frequentist and Bayesian paradigms, where what is happening in the we have big discussion about objectivity of prior information, how it's being introduced. It's not that relevant for practitioners, but from philosophical point of view, it can be rather relevant. So we have generally main 2 points. First one is the option of population interpretation. So the prior distribution represents what are the possibilities of our parameters that we are coming from. What represents, because if our prior is the if our parameter comes from certain distribution, it gives us information where the data can come from. On the other hand, with the priors from, we can look at priors differently, because the population values is one thing. However, the actual state of knowledge in the process might be more vague in this situation. So prior can express our knowledge as it could be some kind of uncertain random information. It is especially important in situations when there's a difference about our cases. Is our case one of many? For example, multiple experiments, we are analyzing one device which is mass-produced, so it is a repeated construction of multiple students. For example, when you are creating a diagnostic model, you have multiple electrical motors, and you want to, so parameters of those motors come from some kind of population of possible situations. On the other hand, there are situations that are naturally unique. For example, every person is unique. So stating about providing prior information about persons' chances of creating a car accident for determining their insurance premium is the issue that that cannot be replicated into a population. So we can kind of provide some knowledge considering from general aspects that we can apply to our individual situation. So depending on the case we have either population or state of knowledge interpretation. Priors then, we've started with prior that provided us no information. We've used uniform prior, which stated in this case our complete ignorance, so it was not uninformative priors. What are, however, informative priors? Informative priors introduce new information. As with population interpretation, can be interpreted as a knowledge from previous experiments. Perhaps we have not used the situation, we have not analyzed the situation before, so maybe we have another situation before, we have some data from before, we can introduce this into the prior distribution. This is especially relevant in the context of analytical computation, because in numerical computation it's not that easy to provide prior from our previous knowledge from previous experiment, for example, our previous posterior as a new prior. But in case of analytical computation, it's rather easy. For a binomial example, we can use a prior for theta that comes from generally previous experiments, from giving us information, as we've seen before, the posterior distribution for initial example was a beta distribution. This beta distribution encoded our information about the probability what theta actually is. In our case, natural prior then, that comes from our previous experiments, is again a beta distribution. If we had a alpha minus 1 prior successes and beta minus 1 prior failures, then the beta distribution with parameters alpha beta is our prior that includes all our previous experiments. Those two numbers gives us successes and failures, or successes and total number of experiments, gives us the relevant information. This is easy to use in our analytical computation, because our posterior then becomes as at least is proportional to a multiplication of likelihood function and our prior. Our likelihood function from the binomial distribution we've seen before, it is here, and our prior is the beta distribution with parameter alpha and beta. As you can see, it is a very nice case that that this form allows us to collect those numbers together, and our posteriors becomes again a beta distribution, but with new parameters. Not alpha and beta, but alpha plus y and beta plus n minus y. And expectation of this distribution, so the mean value of this distribution, is known as with many known distribution, is in this case alpha is alpha plus y divided by alpha plus beta plus n. And this is actually a very interesting situation, because it clearly shows us what is the this expectation is a natural compromise between data from the experiment and data previous to experiments. Because as you can see, this value always lies between y divided by n, so the proportion of successes in the experiment, and alpha divided by alpha plus beta, which is the which is almost the same as the number of successes divided by total successes and failures. We have this actually differs by 1 in the numerator and 2 in the denominator. As you can see, we had alpha minus 1 successes and beta minus 1 prior failures. So in this case, we have number of our successes plus 1 divided by number of all trials plus 2. This is important because our model works in a case when we have no experiment and no prior knowledge. Because in that case, it is our expected value will always be 1/2. So the middle value between all the possibilities, because our possibilities in this case, it gives us some information even in absence of data. This is not possible when we consider only likelihood. In case of likelihood, if we have no data, we have 0 divided by 0. If we introduce the prior information, even if this prior information is strictly uniform, alpha and beta are equal to 0, in that case, we have the alpha and beta equal to 0, but a number of successes and failures are equal to 0, so the alpha and beta are equal exactly to 1, then in this case we have the we have always encoded information that there are two possible results, success and failure, and we can compute expectation from that. This case that I've shown that multiplying prior and likelihood, which gives us a nice formula for posterior, is a very special case. This is a very special case that was very popular in early Bayesian analysis because using that because this property allowed us to do analytical computation. We have analytical form of prior, we have analytical form of likelihood, and getting that we have an analytical form of posterior, which is a form of a known distribution for which someone has already computed expected value, computed variance, standard deviation, stuff like that. In case, this property is called conjugacy. Conjugacy is a property for which we have a case that if likelihood belongs to a certain class and prior belongs to other class, their product always belongs also to that other class. This example we had here, for binomial distribution the beta distribution. So beta distribution is conjugate to binomial distribution. And other examples is normal distribution, where normal distribution is a conjugate to itself. So if we have a normal likelihood with normal priors, the resulting posterior also will be normal. So the conjugacy property is a very nice option which can allow you to do analytical computation, and this is something that older Bayesian books are working on mainly. And for posterior and for numerical computation, can be useful because it can make stuff much faster. That's why we often want to do normal approximations, because we can accelerate computation really significantly by adding that option. However, while conjugacy is nice property, it should not go by itself, because sometimes conjugate distribution is not a proper way to encode the information that we have. That information might be very specific and not possible to put into the context of a conjugate distribution. Moreover, certain distributions can be conjugate, but that does not introduce much bonus to the situation. The best example is multidimensional, or otherwise known as multivariate normal distribution. So distribution over vectors, where there is certain prior distribution for variance of covariance matrix of multivariate normal distribution, which is called inverse Weishart distribution. And this inverse Weishart distribution, while it is conjugate, it is horribly ineffective computationally, cannot be interpreted to encode any kind of knowledge. The only bonus is that you can get analytical computation, but that doesn't give you anything useful, really. Let's make an example of how informative priors work. There is this very nice example from biology. There's a very nice old data set considering something called placenta previa. Placenta previa is the medical condition that is related to the birth of a child. As you should know, from biology in your school, Baby is connected to the mother not only through umbilical cord, but this umbilical cord is connected to something called placenta. Placenta is a part that connects the mother's body together with a child through the umbilical cord. Placenta is something that is being removed after the birth from the body. It's either happens naturally after the birth of the baby, then the placenta is like a second birth of the placenta, or in case of, for example, C-section, physician removes the placenta after removing the baby from the mother. However, there is a certain case called placenta previa, called in Polish łożysko przodujące. This case is when during the birth the placenta goes first before the baby. And there was a consideration that was given that is proportion of girls born with placenta previa is lower than the proportion of general female births in general population. So is placenta previa more rare when girls are born? And the study observed 980 birds with placenta previa. 437 of them were female. So this can be considered in classical case as a hypothesis testing. We will look at in a problem of parameter estimation. We will look what is the probability of the parameter sorry, my dog decided to disrupt the lecture, so maybe that will stop him. At least a bit. Generally, the probability of we are trying to estimate the probability of placenta previa in the entire or the probability of female birth in the group of in this given group. So, if we assume that we have unity from prior, we can get an easily analytical computation that gives us the posterior beta of 438, 544, and we can compute those values analytically, but it can be also done using sampling, and we can get a highest posterior density interval between 41% and 47%, with a median of 44%. So, in this case, we got from the sample, the probability of the baby being female is has a median of 44%, and it's for 94% between 41 and 47%, which is lower than the proportion of female births in general population. That's easy situation. But we have not introduced any informative prior. Our case visualized, we can see here, this is the probability of female birth in placenta previa situation. The probability in the entire group is a bit to the right. We will consider conjugate priors because that will be easy in our case. Because we have binomial likelihood, beta is easy, so we can encode our knowledge, the mean value of the whole population. But we can actually analyze how big population, what is our control population, we introduce to our problem. We can do it rather easily because we can use the formula for the mean of beta distribution. So we can find what kind of alpha and beta has to be to keep the mean at the level of 0.485. However, we still have two parameters, and we can modify it by changing the population size. And we'll do computation using various population sizes with keeping the same mean. So we'll be trying different number of patients in the control group for our prior information. And as we can see in this table, depending on the number of the patients in the control group, we can see that our posterior median drifts towards the value of general population. With, in case of 1,000 patients in the our prior group, we without placenta previa, we included our value for the population of general population has landed inside the 94% credible interval of the posterior. We can see it here that depending on the size of the population, we can start to move from the sample average towards the mean of the prior. The more population is inside included in the prior becomes more and more informative. If there is a very limited population, the prior is not informative, doesn't add anything. We add more patients, it rises. We get even more patients, it becomes more and more strict. If we would go for 1 million patients, it would become very, very thin. This computation, of course, is for the for the conjugate prior, but this is not something that we are limited to. We can do numerical computation in case of any kind of prior, because using computational tools, we are not limited to analytical computation. And for example, we can consider the likelihood using the we can consider our model with a non-conjugate prior, and we can approximate the beta distribution with a normal distribution, because actually we can easily compute both expected value we already knew, so the mean we knew. We can compute a standard deviation of beta distribution also with appropriate formulas. And for case of beta equal to 1000, this standard deviation is 0.016. If we use a normal distribution with given the same mean and computed standard deviation this way, those distributions are almost impossible to distinguish in the 0-1 interval. It actually happens that normal distribution is almost equivalent to beta for appropriately high number of high populations in our case. And as you can see, analytical computation of this is not possible anymore. However, numerically, we can easily see by evaluating the posterior distribution that the computation is exactly the same, and our likelihood drifts towards the prior. So our posterior information is somewhere in between. And that concludes our initial Bayesian basics discussion. As I said, today was a very short version. Tomorrow we will see stationary and we'll discuss the more relevant aspects of general modeling regarding causal analysis in order to help you with your projects that you will be starting in laboratories very soon. So, if there are any questions on the chat, I will be happy to answer them. If not, I can answer them also tomorrow during the lecture. So if you have any questions, please don't hesitate to ask. And if not, we will be finishing in a moment. Okay, so I see there are no questions, so I wanted to wish you a very good night and see you tomorrow with on